start, sir?
Yeah, sure.
Yeah.
Right.
Yeah. So, dear participants, I request you to put on your camera, please. Okay. So, Dr. Kanish, can you please unshare your screen so that I have something to present you?
Sure.
So I would like to take the opportunity to introduce Dr. Kanish. Dr. Kanish Tyagi received his bachelor degree in electrical engineering from GB Pant University of Agriculture and Technology, Pantnagar, India. Then he worked as research associate in Department of Electrical Engineering, Indian Institute of Technology, Kanpur. He received his MS and PhD degree in electrical engineering from University of Texas at Arlington, USA. Currently, he works as lead machine learning autonomous driving scientist at Aptiv Corporation in Agora Hills, California. His research interests are nonlinear optimization, deep learning, networks, and feature engineering. He received IEEE CIS Outstanding Student Paper Travel Grant Award in 2007 and 2011. He has also published a number of quality research papers in various international journals and has a number of US patents. Now, sir, on behalf of Jaipuria Institute of Management, I present you the green certificate. Just 1 minute. So the green certificate is the initiative taken by our institute. On the name of our guest, a tree is being planted at Sundarbans National Park, West Bengal. So thank you so much, sir, for
Thank you.
giving your time. So I request you to take the session forward.
All right. Yeah, thanks for the introduction, Richard. So give me a second and I can share my screen. Let's see if this works. So, Richard.
Yes.
Okay, cool. So
sir,
yeah.
just one second. And I request to all the participants that if they have any, if they feel to ask anything, they can unmute themselves, okay, and they can have the questions in between.
Yes. So yeah. I mean, yeah. Just feel free to ask something in the middle if you have any questions and all. So yeah. The topic I wanna discuss here in this talk is the machine learning in autonomous driving with three specific aspects of it. It's a very broad topic, so I just picked up three parts of it. First is the framework, modeling, and then the challenges that are associated with this, and specific to what happens when you actually put it in the production, in an actual car. So, so as I've already been given the introduction, this is me, and I did my PhD in UT Arlington. Specifically, at my work, I majorly work on radar machine learning, and this is a new area. And our company Aptiv is specialized in producing radars. So now my job is to actually make radars which are heavily specific on machine learning applications, and only to radar machine learning applications. So we don't specifically work on LiDARs as such, but mostly radars and camera. So let's see. So yeah, all the figures in this presentation, I mean, I had to put this slide just for my lawyers and all. So none of this is confidential. Everything is in the public domain, and I've given the references as and where required. So let's see the workflow here. So yeah, in terms of framework for the autonomous driving cars, I'll talk about three parts here. One is the different sensors that we actually need in an autonomous driving, and the sensor stack, and the hardware that we use in the autonomous driving. Different companies have different hardware, so I'll just give a very general overview. Again, nothing is specific that's there. And then how machine learning is actually used in this case. And then the second part of the talk will be modeling. Like, how do you actually use machine learning to model a problem that we have? I'll just take one case study, which is a very sort of an essential part of autonomous driving, which is how do you understand a scene, a driving scene? What are the objects in there? Is there a pedestrian? Is there a moving object, stationary objects, and all sorts of things? And then the third part is majority is like, what are the challenges that comes with it, and my 2 cents on it. Like, what are the open problems, and especially the research problems that are there. It's heavily research intensive area, actually, the entire autonomous driving. So there are a lot of open problems in this that we actually see it in practice. So, okay, so let's just motivate this talk. Why do we actually need this whole self-driving cars? So autonomous driving was started from the one of those early DARPA challenges in the 90s. DARPA is a defense institute from US, which funds all these potential research problems. So Stanford, Carnegie Mellon, these were the initial sort of universities that took part in that. So first they tried to do it on the desert, which is a relatively simple place to do an autonomous, and then they moved it to DARPA Urban Challenge. But apart from that, humans are terrible in driving, actually. If you see the accidents, the number of people who drive the car, and the underage, the drinking, and there are so many problems. So humans are the worst drivers, actually, contrary to what people think. And so having an autonomous driving, the roads get much, much safer. We save a lot of money because, well, a person who is not driving a car can actually do other things. And the amount of gas involved for now, sorry, the petrol involved for now, and the amount of battery that will be used, everything will be highly optimized if a computer actually takes over. You can think of an example of a cruise control. A cruise control, when it was introduced, was not considered a good idea because a human thought that he can, push the gas pedal and save more, but that's not true. And now cruise control is almost everywhere. It reduces traffic congestion because you can predict when the traffic is going to be more, when the traffic, which is the easy route to take in a city. The environmental gains, of course, it comes with it. If there is less fuel being used, then there is better for the environment. Parking lots it's a big problem in the US that there are the huge amount of land is being used for parking lots because the cars needs to be parked there. The model, the parking lots idea is connected to the next point here, which is the subscription-based service. Now, this is where actually the business is heading to. That ultimately what you want, it's almost like a Netflix subscription that's going to be there. You just take a car, subscribe to that car. Volvo currently is doing that on a very small scale in LA, where you subscribe for the car comes to you. I mean, for now, the driver brings the car to you. So ultimately, there will be less parking lots that will be used. And so parking lots places can be used for, for other retail purposes and stuff. So that's the benefit there. So let's see. So to introduce the idea of autonomous driving, let me just break down typical driving tasks that are there. In a typical driving task for a driver, there are basically 4 different tasks. The first is the lateral control, which is basically going in the left or the right direction. So it's either by using a steer to do a lane change, or he wants to park the car on the side like a parallel parking. And then the second is a longitudinal control, where he needs to either brake or he needs to speed up to sort of accelerate on a highway. And then, like I said, cruise control, where he just fixes the speed and the controller in the car takes care of the rest of the things. So it maintains the speed. There is also an adaptive cruise control where, depending on, you define the distance you want to keep from the front car, and then the car actually maintains that distance and also speed up or slow down depending on what, just to maintain the distance. So within a lane, it's pretty much autonomous. The third part is, and this is the sort of the more research part of it, which is the object and event detection response. So once you're driving a car in a typical scenario, and for the sake of simplicity, take a very simple case like a highway, not a typical city or like a Delhi traffic or something. In a typical highway, you see a bunch of things in there. So you assume there are certain assumptions that will be made here. You assume the lanes are there. You assume no animal comes on the road suddenly. You just take care of, like, there are some debris on the road. Either there are stationary debris, like let's say a tire or a wooden pallet, or some kind of like a dehumidifier. Sometimes people throw away their beds. We have data for all these things when we see it in our sort of day-to-day work. And then we have these moving objects, which is basically, let's say there is a car next to our lane, and then we have to maneuver our car in such a way that we don't hit that car, and then we change the lane. So we have to take care of that. And then there is a planning involved. A planning is, let's say you want to go from point A to point B. What is the easiest route to go? What is the, maybe you want to go with less traffic, but it'll take more time. Sometimes that's a preferred route that we have. And also the car should be able to do it by itself. So there is a short-term planning, which is, let's say for a very small distance. And then there is a long-term planning that we need to do, where it'll get quite clear in the next slide, where you have really long miles to go, and you really want to drive without actually sort of interfering with the autonomous driving part. So that's for it. Now, in a typical autonomous driving scenario, the US highway system and even the European highway system, they have defined this into 5 different domains. Currently, we are on level 0, which is the typical vehicle driving system. Level 1 is what most of the cars usually have now, like lane assistance system. I think Toyota has this. Adaptive cruise control. Majority of the cars have this, Honda, Toyotas, and Audis and all. And then you have this level 2 systems, which is where the amount of complexity of the problem actually exponentially increases as you go along the levels. So level 2, where you can actually do both the lateral and the longitudinal control. And like, for example, lane changing, how to steer the car automatically. And right now, Super Cruise is one feature that my company, Aptiv, actually provided to GM. So that's one place where it's being used. Level 3 is where you include the object detection parts. So you say, hey, there is some object in front of you. Can the car automatically take care of that? So that's what we call it, OEDR. And I've tried to reduce the number of acronyms in this slide, but believe me, in autonomous driving, there's too many number of abbreviations and all that we have. So OEDR is one frequently used, that where you have an object and you want to see if the system is able to detect and what response it has. And then in case it tells you there is something ahead of you, the user or the driver has to then take control of the vehicle and then take care of it. So Audi A8 is one example of it. Level 4 is, again, has everything what level 3 has, but instead of giving it back to the user, it can actually take care of itself and it can maneuver it by itself. Waymo from Google, those guys are doing this right now. And in certain cities like Mountain View and in Arizona in Tempe, they're actually able to do this level 4. Level 5 is where everything is going to head, where you literally do not have to touch the car. And as I'm showing it in the picture above, you can see you don't have to touch the car. There is no driver actually there. It's going to take a while to reach level 5. And there are a lot of challenges and sort of open questions there, which I'll be discussing here. So let's see. So just focusing on this object and event detection part, I just gave a couple of examples that you see on the road. Well, this is a typical scenario, like a dog or a pet or an animal on the road. There are some debris on the road, which is from a prior accident. That's quite common. You have some kind of a landslide or some kind of a construction happening on the road. And then you have to understand the speed limit. Now, this is a very typical case. You have to understand the speed limit, and then you have to make sure that you drive the car within the limit. So these are all the things on the road. And there are multiple things. And I've not included, let's say, the traffic lights that are there. There are a lot of things that are on the road that you need to make sure that you are able to detect. But when you go into in the production part of it, when you actually put it in a car, you not only have to detect it, but you also have to somehow fuse all the things together. And that's a tricky part. Like, how do you do the fusion of all these decisions that each of these systems are making? One is making object detection, one is making lane correction, one is making the lights that are there, the green light, the signal lights, how all these things come together. And then the system, the car, is actually able to make a final decision. So all these things have to come together. There are a lot of neural nets, deep learning networks that are being used. Again, most of them are proprietary. One of them that is still open is HydraNet that is being used, where it just combines all the decisions from different neural networks and then give a final decision. So, like I say here, there are stationary objects, moving objects, and near moving objects. So near moving objects, you can think of it like a pedestrian who is either moving or not moving or going at such a slow speed that it's almost stationary. Imagine you walking walking in a mall or something. So, and based on this, you need to have some kind of an appropriate response to this. So this is one of a typical setup in one of our in one of our cars here at Aptiv, where you have all the sensors in the car. This is just a very overview kind of thing. There are a lot of more hardware involved actually. So you have all these radars in the front. We divide the radars also in different parts. So the front radar you see here, this is a long range radar. By long range, it's almost like 250 meters that you have. The side looking radars are the ones that are 100 and 150 meters, which mostly are used for what's in the next lane. The front radars are mostly used for what's the object in front of us in the lane. And the cameras are there for detecting, the front cameras are there to detect the light, the signal lights that are there. And then again, the back camera, the LiDAR is on the top. LiDAR is a very controversial sensor. Some companies like to have it, some companies don't. So I'll be talking about this in more detail later. And then you have an IMU, which is basically a measurement unit, which kind of tells you where you are in the world coordinate system. And then you have the back radars and all that are used for what's coming from behind. So one use case of a back radar is the car is driving in your lane, and then suddenly there's a truck coming from behind at a very high speed, and it's about to hit you. The radar on the backside should be able to detect it, and then quickly speed up in order to avoid the collision. We see these kind of problems a lot in logs that we see. I mean, in the data that we see, and we collect data from let's say from very crowded places like Singapore, Boston, and a couple of highway situations like in the US and Germany. So all sorts of different scenarios that we have. So let's see the basic framework. Now, once we have established some of the basics. So what is the sensor stack that we have? So what are the typical sensors that we actually use in AD, in autonomous driving? The first one is the most common one, the camera. Now, it's the cheapest sensor available. It's easy to use. People are more trained on camera. And in practice, when you hire machine learning scientists or engineers, most of them have a vision background. So most of the people are very familiar with the camera. So, and then you have to move on to the different other sensors and all. So what are the comparison metrics that we actually use for this? First is the resolution that we have. So how much are we able to find the details in a camera image? That's something we need to check once we install a camera. And we are talking like 2 megapixel or like maximum 3 megapixel cameras. We're not talking some fancy camera. Because cost is a major player when it comes to what goes into the car in the end. And just to give you an example, I mean, BMW loses they reject a contract just on, let's say, 10 cents per radar or per camera, just on 10 cents. That's enough for them. So because they're doing it in millions, the number of cars and also it kind of scales up. So cost is a major factor. Then you have the field of view in a camera. How far can you see the things and all that you have, and how much width of the angular that you have. Then you have the dynamic range in a camera. The dynamic range is you can think of it like a difference between the most dark part of the image versus the most bright part of the image. So how much is the range? How much of different objects I can see? So dynamic range mostly gives us an idea of how many different objects can I see in a camera. The problem in a camera is, well, it doesn't work well in situations like fog and rain. Now, from a car manufacturing point of view, we are supposed to sell a car in every climatic situations. So think of it like any Scandinavian country, let's say Sweden. There is a huge amount of time it's just raining all the time. Most of that is fog. You cannot sell a car there. So a camera by itself is tricky. And then there is a depth estimation that we can do with a camera, where we use a stereo camera, and I'm showing it here in the left image on the down, this one, which is mostly used for depth estimation. But this part is more of an alternate to a LiDAR, because that can also do a depth estimation. So that's one sensor that we have. The other sensor we have, which is where I work on intensively, is the radar. They are very good for moving object detections, and radars are there for a long time. They started during World War II in their development stuff. And automotive radars are majority of the time they're being used for parking or for very short range radars. So still you don't see that many long range radars in production. And there are different reasons for that. So if anybody's interested, I can go in details there. The comparison matrix that we have here is how do you see what is a good radar? So you see, okay, what's the range of the radar? How far can it actually detect things? What's the field of view, which is if you think of a polar coordinate system, it's basically the azimuthal angle that you have. And then you have the position, which is the range, and the speed accuracy, which is they call it in the radar domain a Doppler, which is, or they call it range rate, which is how fast the things are going. And radars are very good in determining how fast things are going. And that's the reason why most of the cops, when they try to detect how fast a person is going, they actually use those radar guns that are there. The disadvantage of radar so far is that detecting a stationary object is very hard. Now, an example of why do we want to actually detect a stationary object on a highway, let's say, is think of a situation like where there is an ambulance parked next to the highway, and this was actually a case with one of the Tesla accident that happened like 2 years ago, where an ambulance is parked on the highway. The Tesla car is in the autopilot mode. The car goes straight and just collides into the ambulance because the radars are not able to detect the stationary ambulance car. So radar by itself have a bit of a problem in this, and that's where majority of the research actually happens. Like, how can you detect stationary objects from radar for a very, very far range? And again, I'm talking, let's say 200 meters or 250 meters. And then the second part of disadvantage is something that I see it time and time again. It's very hard to hire like quality radar engineers because it's related to defense, and people who are good in radar are not good in machine learning, and vice versa. Like, I myself come from a vision background. So that's one problem. The third sensor that we have on a car typically is a LiDAR. It's majority based on laser, and it detects on the same idea that the radar is using. Radar is having electromagnetic waves, LiDAR is having a laser. But this one creates a 3D point cloud, like you can see it here. It creates these 3D clouds, so you have a very good depth estimation here. And now again, how do you determine what's a good LiDAR? You find out the number of beams that are going in. So the number of beams, think of it like how good the resolution is. Think of it that way. The points per second is, again, how fine the point cloud is. So the more the number of points per second, the more detailed or more granular image you can see. And the rotation rate is pretty much there are a bunch of lasers on top of the car, like I'm showing it here. And then the higher the rate is, the more the things it can detect. So you can think of it like if there's a higher rotation rate, it can detect very fast moving objects because it's able to actually, throw the laser at it and then bring it back and then detect it. So, but not just on the top, actually the LiDARs are also used on the side. So this is one of our cars that we currently is in production. It's in Vegas. So if you order in like something like an Uber, then the Active Cars actually comes and picks you up. So it's pretty cool, and it works, and that's a good part. So yeah, the disadvantage is it looks very ugly when it's on top, actually. So think of like a Porsche or let's say a Ferrari, and you think of a LiDAR on top of it, nobody's going to buy that car. And so that's actually a big problem. And customers reject a car just on a minor scratch in a car. I mean, it's how picky people are. But it makes sense that they're paying for it, so they should be. And then they're extremely expensive. Like to give you a price range, Velodyne is a famous, is a well-known LiDAR manufacturer. They work with Waymo, and those guys are selling it. And I'm quoting the price from 2019, $1,000 per piece. And to give you an idea, a typical adaptive cruise control that is sold to a customer, which is only using radar, is roughly around $2,000. That goes with the package when you buy the car. And it actually costs a company, let's say $10. That's it. So that much is the margin. I imagine if $1,000 is the cost, how much is going to go to the end customer. So again, that kind of defines how the business actually works for us, because what we do is we mostly work again with the high-end cars and high-end customers, because somebody who's buying a Porsche, let's say, or let's say a Ferrari, or even an Audi, can easily afford a $2,000, $5,000 package because he's buying such an expensive car. So mostly we go with that, and then it kind of trickles down to sort of other cars that are there, let's say Toyota or a Honda. Now, a good thing in LiDAR that's happening recently now is the solid state LiDAR, which is not this whole ugly looking thing on top. It's something which is on an FPGA, on an embedded chip. And that can be something that can be a game changer. So we have to see. That's again a research area that's still there. Now,
Just a question, sir, for this.
yes.
Are these laser lights are harmful also for the outer environment of the people in the surrounding?
Not really, because unless you're like literally looking at them with your eyeballs, I mean that's a different thing. But not really, they're not. I mean, detecting objects with LiDAR is not a new concept. Putting it onto a car is still new, and it has its own challenges. But not really, it's not that harmful. I mean, it's not. At least the studies that have been done, they're not harmful. So,
Dr. Tyagi,
yes.
You said the LiDAR is coming on an embedded chip now. Does that go along with the front sensor, or is it still mounted on top of the car? How does
Oh
it?
yeah, so that's something. So they're not trying to put it on the tub again because of the same problem that it doesn't look nice. And different manufacturers or OEMs are betting on different things. So Aptiv works with the majority of all the three German manufacturers. So BMW, Audi, and Mercedes. They don't want to put a LiDAR on top. So the solid state is something that's going to be inside within the frame, either on the front bonnet or on the back side. But so far, the studies that have been done, at least the papers that have been published on this, on the solid state LiDAR, this is mostly for short range LiDAR detections.
Got it.
So you kind of lose the long range part still. So,
Understood.
And companies like Tesla, I mean, that's on the other spectrum, on the other side of they don't want to use a LiDAR at all. And the Tesla, the car that they have, they don't have a LiDAR actually. They only have cameras, mostly majority cameras. And then radars are only for very short range radars, parkings and very small objects. But majority of things they're doing it with the camera. Waymo is betting high on LiDAR. So that's the scenario.
So Mr. Tagi, the Doppler you have described, are these the radar are Doppler or something else?
Yeah, that's a Doppler from the radars.
Okay, and the sensors you have described, these all are mounted outside the car. Is there any sensor to manage the engine or some inside the vehicle system?
Oh yeah, there. I mean, the car by itself has as a dedicated embedded chip that's doing that. But here I'm only talking about sensors that are specific for autonomous driving, and not for like, let's say, consuming like efficient engine consumption of the gas and everything. So those are separate sensors. And I'm not including in this talk, but actually it's going to take a while, but the plan is to actually put a GPU on a car. That's going to solve a lot of problems, because think of it this way, that you're now increasing the amount of things you want to take out of a sensor. So you are increasing the computational complexity. So now you have to increase somehow the embedded part also. And I'll go into the embedded part later in the talk.
Okay, so to control all these things, only FPGA is using, or some microcontroller processor is there?
There is an FPGA and there is an embedded like microcontroller by itself. But I said it in the starting, every company prefers their own. They want a complete control over it. And the reason for that simply is we went with NVIDIA first and Qualcomm to give the.
Are you going to explain the configuration of processor or something like that?
I'll just briefly mention that, the contribution of that. But what I can tell you is like, it's highly proprietary for every company. And the one that are in the public domain is like NVIDIA and Qualcomm. But they charge so much of whatever the commission that they need for that, for each of those. It's not viable for a business. So it doesn't work. Still, some companies are actually doing that for their high-end cars. But the amount of share that they need, it's kind of too high to make business sense.
Okay. If we want to configure all these things with the Raspberry Pi, is it feasible?
So there are two, yes and no. Yes, it's feasible, but no, because it's not industry standard. Like you have to think of, is the Raspberry Pi able to work, let's say in -20, -40 degree? Is it industrial grade or not? Can it run? Is there any misfiring happening? Is there any misclock that happens? You have to think of a lot of other things. So there are a lot of approvals that you need to take. So Raspberry, or let's say the one that actually works, that we have we actually work on first when we go into the embedded, is the Jetson, the NVIDIA Jetson. That seems to work pretty well. Not saying Raspberry doesn't work, but Jetson seems to work pretty well. The library is much more stable from NVIDIA, and that one seems to connect much better to all these sensors. And you can actually put your algorithms in there. Make sure the sensors are working. You can time it correctly, so you can do that.
Okay, and what about the power supply?
Yeah, so power supply so far, I mean, it goes through the battery of the car when you actually put it onto the car. But there is a whole there is a completely separate hardware team that actually is dedicated to just make sure that the most tricky part is actually the data logging part. I can go more in details of that, but just to give you a very quick idea, each frame of one of those radars that you have, so we are talking around 500 megabytes per second of information coming in from just two sensors, let's say a camera and a radar, and you have to process them. So there are like two companies so far that are able to sort of successfully demonstrate that yes, they can actually log this data. Otherwise, you start having missing frames. So that's why we need our own operating system that actually handles all these sensors together, this entire stack.
Okay. So there was two news earlier I have seen. Like yesterday there was news that autonomous vehicle is confused by the moon. The moon is understood by like vehicle as recognized as like traffic light. And the second news was like 0 was recognized as 8. So
yes, those are like edge cases and all. I'll be talking about them in the challenges part. Yeah. This is more like these are all edge cases and all. And again, like these edge cases are the sort of the research problems that are there.
I will discuss more. Let me see.
Yes, please. Yeah, I would love to discuss it. Yeah. And thanks for the question. Thank you. So,
Dr. Pranav here. You are not covering two parts, what I see. I mean, one is like infrared, and one is like multiple cameras, which are also being used in the current research, right? Is this presentation from the standpoint of the company which you are developing, or?
No, it's mostly from the standpoint that what actually goes into production recently. Infrared and something it's already there. So I'm just specifically going with what goes into an autonomous scenario of a car. So like the ultrasonic, I'm not going to cover, let's say, the ultrasonic sensors.
Yes.
And that's majority, because most of the time, or majority of the time, ultrasonic sensors are used for parking. Right. So I'm not covering, let's say, automated parking situation. So, but nothing against those sensors.
Okay, fine. Please go ahead.
Yeah. Okay. All right. So, so far I just talked about these three: camera, lidar, and radar, which are on the outside. we have these two sensors which basically tells us in summary where we are in the world. And these two sensors are roughly used for path planning and the maps that we have. We have different kind of maps in the autonomous car. Again, I'll not go into the details of this, but the map guys and the path planning guys, they use this GPS and IMU information from the car. And then we have this sensor, which is highly used for calculating, again, what's the orientation of the car in the whole coordinate system, and then it tracks the vehicle velocity and all. This is the same odometer that we actually use, how many miles the car has been driven. So that's there. So again, I bring back the picture again just to emphasize, okay, where all these things are set up into the car, just to remind. And again, this is not like a very permanent way of actually putting these sensors. There are a bunch of sensors that are put into the car depending on what's the kind of task you want to do. If you want to give a demo to a customer, there are much more sensors than this because you don't want anything to go wrong there. So this is another, and like I said, there are much more sensors. This is one more case I'm showing here where we have these many number of sensors onto a car. And this is what we have in the Consumer Electronics Show in Vegas every year, where we have to showcase the new features of a car. And these are the number of typical sensors that are involved. Again, this is again in the public domain. Just you can quickly do a Google search on this, you can find this. It has all sorts of camera, radars, lidars, GPS antennas, and a bunch of hardware and software stacks. Okay, so let's get into the hardware part of it.
Doctor, what is the role of the trifocal camera? What does it do exactly?
That's mostly for the traffic lights that are in front of you,
Okay,
and then something that's right in front of you. So far traffic lights, and then sometimes for the pedestrian. But right now there is a good amount of research on doing pedestrian detection using only radars. So that way we can actually detect it in fog, rain, or night conditions and everything.
Understood.
So that's the research.
Thank you.
Okay, so yeah, let's get into the hardware stack part of this the autonomous driving. The hardware stack is again, it's custom made, it's highly proprietary, but these are the ones that are in public domain. The job of a hardware is, in this case, is all sorts of sensors that are there, and I mean like not just the lidar and like the one that are on the outside, all the different sensors, even the ultrasonics one. Everything goes into the system, into this hardware, and then it spits out whatever decisions the car has to make, like maneuvering the car longitudinal, laterally, or it detects an object, stop the car, all sorts of things. And then when does it have to give the control back to the driver? All those decisions are made, and this is fairly complicated. So as a research area, embedded machine learning is the next thing from what we see in the industry. That where more development, more research needs to be done. So like I say here, the top one is the Mobile IQ. This is it's fairly industry standard. It's currently being used in a couple of OEMs. And the second one is the NVIDIA that they have produced. I'm not quite sure. They have not sort of revealed which all OEMs are using it. But earlier Tesla was using this NVIDIA in their first generation of their Tesla cars. And then they moved on to their own chip just to have the complete control over it. And the other hardware that we have while we do this whole autonomous driving is how do you actually train these big deep learning networks and everything. So we have what we call is like a offline hardware. And first you have regular, like the normal workflow is you have a laptop, which has some kind of a very decent GPU. You do a proof of concept on that, whatever algorithms that you plan to work on. You move on to a very high-end station. Like here, I'm showing the, I believe it's the DGX NVIDIA machine, the second one. You also have Lambda machines, mostly that are used in the corporate. And then you have data on the cloud, or you have it local. But majority of the time, the companies are moving towards doing all the computation. In the end, once you have it on the workstation, the things are running with a decent amount of data. To do the massive parallelizable training, you move it to the cloud. I can give you in my experience the example. Most of the OEMs is what I call, they're coming from the Detroit culture, like mostly from the Michigan area. And those guys are a kind of different culture than, let's say, the Silicon Valley culture, which is where I come from initially when I joined the company, where it's more of very fast paced. You want to make mistakes and everything. And, you know, it's kind of a very different culture, these two. Still, people are resilient towards actually putting things on the cloud, and they want this big system sitting next to them so that they can see a computer is running and they say, okay, things are working. So majority of OEMs find it hard to move as fast as, let's say, an Apple or a Facebook or, you know, all the Bay Area companies that are there. So that's one problem. But in a general sense, offline hardware is where a lot of capital goes of a company, and most of the data logging, data collection, training, and deploying, all of this happens here. And then last is, I just put it as an example here, a synchronization hardware. When you have all these sensors in the car, what you want is some kind of a common clock on which all these sensors are working. So the timing is very important. Like each frame that comes in, the sensor should be able to figure out, this is the frame that I need to analyze, whatever sensor that is. So most of the time in practice, GPS clock that is there, the clock that is there on that is what we use in production when we put the entire software stack onto the car. Now, let's put the role of machine learning in the autonomous driving. Now we know all the sensors that we have. Let's just take a case of how the first step for any machine learning is the data. So the way we actually store data is the way the driving environment is. So the first case is a highway environment, and the other is an urban, a city environment. They are relatively very different when it comes to the kind of actions a car has to take. In an urban environment, or let's say a highway environment, the amount of cars are more, the speed is higher. We are talking like 100 miles per hour. And the number of them are vastly more, like it's like 12 lanes, 10 lanes and all. The number of intersections are less, but there are some exits that you have. But they're not that much as compared to an urban setting. In urban settings, the lanes are relatively smaller compared to a highway. The standard the lane width is 3.6 meters in US, and I believe it's I'm not sure in India how much it is, but it should be pretty standard. The traffic volume is comparatively lower, and the speed is smaller, is quite low. So the sensors need to react in a different way in an urban setting as compared to a highway setting. So, and that's how you actually store the data in two separate settings. One is a highway, the other is an urban setting that you have. Now, this is just one case I wanted to showcase where, just to give you an idea how complicated is such a simple step is. When you're doing a highway maneuvering in a highway setting for this car. So imagine this is the autonomous car that we are having, and it wants to change the lane. So there are three main steps that it needs to do. One is like, what if the front truck suddenly stops? So it has to do an emergency stop, which is the first one. The second is it has to maintain a safe distance from this car, the front car. And the third is, which is the tricky one, is the lane change. So the lane change is a tricky problem here, because imagine this car going to the left lane, and it also has to see what happens to this car here on this side. Can everybody see the hand cursor on my screen?
Yes, we can.
Yes, sir.
Okay, cool. Okay, cool. So yeah, so imagine this car going in this direction on the left lane, and this car comes onto the right lane of itself. So this autonomous car not only has to change the lane, it also has to make sure that this car does not come into the right car, otherwise there will be collision. A good case, if anybody is interested to actually see this, is United States Postal Service trucks runs from LA to Dallas in a completely in an autonomous way. And the company that's working for them I forgot the name of the company now, but that company developed this solution, a very decent solution, very neat solution to handle this kind of situations in all sorts of situations. So if anybody is interested, I can go into more details, or I can give more details for that later. So that's, and this is just lane changing. So you can imagine that such a simple case has a lot of steps involved. So highway maneuvering is a little tricky, and then the more tricky part is the urban maneuvering when you have to do. So I just want to show, like, this whole problem is very difficult actually to solve. Okay, so let's see the pipeline that we have, a typical pipeline. I'll assume that everyone has a little bit of basic understanding on machine learning and how does these simple, like, let's say, cat and dog examples work. So you have this, so you start with this data lake, an online or an offline data lake, which is pretty much all the data that you have. You dump it into one place. It's mostly the cloud that you have, the cloud storage, because you don't want to have these petabytes of data on these hard drives and all. And just to give you a funny example, it takes more time for us to upload these petabytes of data online. Let's say I want to transfer some data from LA to Germany, in Berlin. It takes more time to actually upload and download the data in Germany than actually ship the hard drive by FedEx. And same problem happens with recently with Amazon. It's easy for them to actually drive a truck from New York to Seattle than actually upload and download the data between them. So it's a huge amount of data that we're talking, petabytes that we are saying. So mostly you store it on the cloud. And then you also have these labeling needs to be done, because majority of the ML algorithms that we have are supervised learning based. Labeling is another place where most of the capital goes. And the labeling that's involved here is mostly semi-hand or semi-human. A lot of labeling tools are there internally with the companies, and most of the companies have their own, or they outsource it to other third parties that we have. You have this data, you get this data label, you train the system, and train it on sort of different scenarios that you want to have. All these, and this data, when I'm talking about data can be coming from any sensor. So just imagine this from, I'm just taking a very broad view here. Any sensor data that we have, you train the system, you test it in this here and here, and then you do a simulation, a data simulation. This data simulation is a new thing that started because the companies, majority of the companies on autonomous driving find it very hard to just keep logging the data. We're talking 100 million miles, or 1 billion miles that Waymo did recently, or Tesla is doing, and all sorts of other companies are. My company does it too. It's kind of really hard to do that in real life, because the amount of cost involved with the driver and everything. So you have this simulated data like a video game. You have the simulated data. Whatever the network you have trained, you put it onto a simulated data to see how does it actually perform. I have not shown it here, but actually there is a feedback loop which goes back to train the network again based on what errors you get in the simulation. And then ultimately, once you have done the feedback loop and you're satisfied with what kind of data, what kind of model you have, you store the models. So this model store is, think of it like a repo. All sorts of good models are stored here in this repo. And then you pick these models, and then you do a deployment onto the car, onto the actual car. And then you drive the car in different scenarios that you intend the algorithm to work on and see the performance. And then the loops keeps going. And then you sort of collect more data. Depending on how the car performs in real life, you see what kind of more data do we need. And then you collect more data, and then the cycle goes. So that's a typical pipeline that we have for a machine learning application in autonomous driving. So I've taken this from one of the courses online. I found this quite interesting. So people who wants to be getting introduced to autonomous driving, I would recommend this. It's a pretty cool course. I'm not in any way associated with them, so just my own recommendation. So what's the software architecture for a typical autonomous driving? Now you have all these sensors. The sensors goes into some kind of a perception and mapping. Like I said before, mapping is a very important part. Perception is where a majority of the the game is going on. This is where majority of the papers are published, and this is a very hot area. of perception. And I'll actually discuss perception later in the talk. And this goes into a motion planning of how do you want to plan the car route that it wants to take. And then there are actual controllers. Think of it like a PID controller. And then gets into an actuation. So I'll not go into the details of each of these blocks. I just wanted to show, just to sort of feature how the software architecture is made in the autonomous driving. So I'll just discuss this specific part of environment perception. Just one second. How much time do I have, Richard?
Sir, you have 35 minutes.
Okay, cool. So in an autonomous driving setting, ML is used on different subparts in different sort of blocks that we have. And as an ML scientist, it's part of my job to sort of figure out where can we actually improve the existing idea and add ML to it and improve the idea, improve the entire thing and the overall product. So the first place is the perception and the localization, which is sort of the most commonly placed sort of use where the deep learning is used.
So can you put it on presentation mode? It's easier to view.
If
you don't mind.
No, I don't mind,
Sorry,
but I have to. You have to help me out. How about now?
Yeah, just yeah, a little better. Yeah, makes sense. Thank you.
Let's see. Oh, I see. I see. How about now? I think
Yeah, perfect.
Yeah.
Thank you.
Okay. So yeah, like I said, ML is used on different sort of subdomains in the autonomous driving. I'm just, again, it's just for sake of simplicity, I'm just showing 4 different parts of an autonomous driving: perception, planning, a low-level path planning, and the motion controllers that we have. Now, there are 2 approaches that have been taken in the applying ML to the autonomous driving. One is each of these blocks are separately handled by a separate network, and that's what we call sequential planning that we have. The other approach that has been taken is that you just combine entire thing and think of it like a black box. Feed in the input, have the outputs, and let machine learning or whatever the deep learning that you use, let it figure out what is there inside. Let it do the planning, let it do all sorts of like the path planning, control, everything. Each of them have its own advantage and disadvantage. I'll just go through very quickly. We mostly work on this part. My own experience has been that it's better to do it block by block, because if there is any problem in any of the blocks, you can actually isolate that problem and then figure out the solution, rather than doing it inside this whole end-to-end thing. Because inherently, neural networks, like on which what the deep learning is based on, it's very hard to understand how does a network learn something. And that part is still an open-ended research problem. So until we get that part, I mean, there are a lot of good papers on them, like how does the gradient works and how does the optimization algorithm is working while it's being trained. But it's an open problem of how exactly the learning happens in a neural network. So because we don't know that part, it's better to do it this way, where you just break this into block by block, and you just do each block training separately, and you can isolate it. So that's one way. But then again, every company and everyone goes by their own, like end to end or like block by block. So there are different ways of doing this. So let me go into the modeling part now, which is where I'll just go into more details of perception. So what's a perception? Well, perception is where how a typical car senses what environment it is in that particular time. There are a couple of tasks that we have in perception, which I've pointed out here: detection, classification, tracking, and segmentation. Detection can be anything, like object detection, moving object, stationary objects, and all. Classification is, again, I'm showing it here. Sometimes you're in. Is there a question? No. Sometimes you're interested in what kind of object are you looking at? You're looking at something. Let's say there is I mean, it's quite common to have some big truck standing in front of you in a stationary domain. You want to figure out what is it exactly that's in front of you, so that you can see if you want to stop or not. Sometimes there is a Coke can or some kind of like a beer can on the highway. You want to see that, and you might want to detect it, and you're like, okay, I can drive over it or not. So under drivability, over drivability, those kind of situations. So we go through that in the classification and detection. Tracking is another way where the most common place where tracking is used is the lane changing, as I was mentioning before. You need to track not just your vehicle in front of you, you also have to track the vehicle which is in the next lane to you, or the next to next lane to you. And segmentation is, again, this is highly used in the urban setting where there are a lot of things which are sort of there in an urban setting compared to highway. Highway doesn't have that many objects. So segmentation, think of segmentation like, let's say, a semantic segmentation or instance-based segmentation. So again, I've taken this from that online course, which is kind of pretty cool. But here, what it shows is the software architecture for a perception. I'll just quickly again go through this. The dynamic object detection that it says all the three sensors, the major sensors that are there, it ultimately, the way it actually does a perception is it just puts a bounding box on top. Now, there are ways of putting bounding box onto an object, and there are ways of putting bounding box in an image or a LiDAR or a radar, or combining two sensors at a time. So there are different ways of doing that. And then once you have a bounding box, you can do a tracking, and then you can do some kind of a motion prediction of it. One thing that it doesn't show here, which I would say is again an open research topic, is can you use a radar or let's say a camera and do some kind of a static object detection, and then somehow transfer the information from this sensor domain onto the other sensor domain? So as someone pointed out here, the infrared sensor. Infrared sensors are very good, let's say, for detecting in certain environment, let's say environment A. Radars are good in, let's say, environment B. Is it possible to actually do a transfer learning from environment A to environment B? There are a couple of papers on them. One good paper I recently read was something called wormhole learning. It's from Zurich, somewhere in some research lab in Zurich. Those guys are doing these intra-sensor kind of transfer learning things. So that's a very sort of a promising research area that is there. So again, I'm showing it in more detail here. How does the perception look? All sorts of different tasks that we have in a perception here. And I'll just pick up one of the tasks and go into details of object detection, which is the most common perception task that we have. Lane detection is another one, traffic detection, traffic light detections. And again, all these tasks requires heavy labeling. So that by itself is a problem. So when you have something in a product, in the end, we need to see from a product perspective, do we have enough labeling, and do we have enough examples taken so that the neural network or the deep learning that you're using can actually generalize? Because that's a very it's a very, very important part, because the edge cases are the one that takes time. So I'll talk about a few edge cases later in the talk. Okay, so let me just quickly go through what are the common models. Again, if people are familiar with these, I'll just skip through them fast. This is a sort of a de facto standard for image recognitions, convolutional neural nets. I'm just showing one example of a let's say this kind of a vehicle which looks like a car, but a car detection, and it'll sort of detect whether this is a car or not. Now, just to give you an insight of a convolutional net, it's shift invariant, but that's not just the only good property. The most important property of this is it kind of keeps the structure of the data inherent, like intact. One argument that's usually made is like, well, why do we need to switch from a multi-layer perceptron to a convolutional net? Why can't we just feed this input as a string of vectors into an MLP, like the way we do it for MNIST examples? And why can't we just do that? And the reason for that is when you do that way, when you break it into a vector, like an MNIST example, you are actually breaking the entire structure of the image that is there. In this case, you just have a kernel which you just slide across, or as they say, convolve it onto the image by itself. So you don't break the image in any way. So that's one of the good properties of CNN. And I'm sure people know here, there's a good amount of research, there's a fair good amount of research on CNN. So here I'm just showing it just for a classification task. Again, this is another one that we use, a recurrent neural net or any kind of a variation of a recurrent neural net, an LSTM, attention-based transformers, all those deep learner models. Sorry for the pixelated image here. I took it from a quick Google search. But the idea is this. Sometimes in a simple convolutional net, you do a prediction frame by frame. So you don't have some kind of a memory involved there. You don't remember, let's say, what happened in the 10th frame in the past. You don't have a memory of that. You just go frame by frame. You decide frame by frame, whatever comes in front of you. If you want to put some memory in it, into the network, recurrent neural nets is sort of the way to go. And again, there are a lot of variations of it, and there is a whole bunch of combination of CNN and LSTM. An open research problem on this LSTMs are when you combine convolutional net and recurrent net in such a way that convolutional net works as a feature extractor, and recurrent net, or LSTM, let's say, works as taking care of the memory part. In that case, let's say you have this huge amount of data that you have stored because you've driven miles and miles. And can you somehow summarize that data into some interesting small little clips that you can actually see later on? So think of it like you have a whole movie, like a Hollywood, like a Bollywood movie, and you just want to have a trailer of it. And the trailer is cut out by a neural network where it picks out the interesting parts of the movie, puts it all together in a sequence. But so you see there, it doesn't not only just have to take out the interesting parts, but they should be in the sequence. I mean, you don't want the climax of the movie all the way in the end, in the starting, you know what I'm saying? So you want it in the end. So the same way here, you have this huge amount of, let's say, 100 gigabytes of data. Can I make 200 megabytes of a movie out of that 100 gigabytes? That's one where open research is there, where can you just do that or not? It's an open problem. There are a bunch of labs that are working on it. UT Austin, there is a lab there that's working on it. Dr. Christine is working on this interesting problem. There are a lot of other people. So I can go into details again if anybody needs. So these are the, if you want to sort of foray into the whole deep learning, these are the must-know networks that one needs to know. I'm sure people might be familiar with this here, but the first one is the LayNet, which is the original convolutional idea came from there. This is a 90s paper. It was sort of again gained traction after once the AlexNet came in 2012, when it won the challenge. And think of this, the place where AlexNet actually won is almost like a computer vision Olympiad kind of thing. So that's where the entire deep learning revolution started. GoogleNet is another very important network or the model where it included the idea of inception. He's one of my collaborators, Christian Skerry, who worked on GoogleNet. So there's a lot of insights into GoogleNet, and I can go into details of it, but if the time permits. VGGNet is another famous one that people use. These are all used in this ILSVRC is the competition that happens every year. And then ResNet is kind of something that we use in production, where you have these residual networks. The gist of the ResNet is that if you have really, really deep network, let's say 50 layers deep, how can you train that network? ResNet has the answer there. How do you train it? So the paper that was published, the original paper on ResNet, kind of gives you that answer. It's so yeah, that's one, and it's published from Microsoft Research. Again, these are the must-know network structures that I'm just putting it in summary here. What all structures that people put in. So what I'm talking here is you have all these convolutional layers and the recurrent layers that you have, but now you have to put them in such a way that actual learning can happen. So these are the different ways that actually people put in different forms to learn different tasks that we have. So it's not like one network fits all, as it famously is called no free lunch theorem in machine learning. So residual networks is the most common one that people use. Dense connections is another one that is actively used. Again, pyramid pooling is something that is used in the fusing two different sensors or segmentation tasks. And again, you can read the paper here. It's an excellent paper to review. Okay, now let me get into the driving scene understanding that's there. As a case study of a driving scene, we want to detect the objects in front of us that are there, different kind of objects and different scenarios. The convolutional nets is again which I'll be discussing here because it's pretty much widely used in the industry and in academics. The image data is what I'll be taking without getting into complications of radar and the LiDAR data. I'll briefly touch LiDAR data just to sort of give a hint of how it is being used in practice. So let's see. This is an example from this paper, as I've mentioned here on the bottom. This is just a camera-based 2D object detection. There are a lot of different detection algorithms that are there, and these are quite successful actually. And one of the main reasons that I found that they are actually successful is the ImageNet data set that is available is kind of so wide that it pretty much covers every different image that you can sort of think of, like every image. So think of image like more of a distribution. So maybe at the end of the talk, I can go into details of it. There are a lot of interesting insights into why this camera-based object detection works better than, let's say, a LiDAR or a radar-based. So what's the reason for that? So there's a good amount of interesting insights. I can go into details of it later. So you have this single stage detections. Famous one is YOLO V3 that is commonly used, the SSDs, corner net. These are single stage. So basically they are pretty fast, but they're not that accurate actually. So, and it kind of detects all sorts of, it's not able to detect the occlusions basically. And then you have these double stage detectors. Famous one is the faster RCNN. That's very much in use. The ROI candidate, ROI is a region of interest here. Whatever is a region of interest that you have, you just first find those ROIs, like the different ROIs that you have. And then you do a bounding box classification in the end. So there are 2 steps involved. That's why they call it double stage. When it comes to putting it onto an embedded, SqueezeNet, MobileNet, these are publicly available. And like I said, every different company has their own sort of their own networks that they put it onto the embedded for different tasks. But MobileNet seems to be very successful. I worked on MobileNet during one of my interns. And this is actually being used in Google Pixel, Pixel 3 those days. So I don't know the recent one that they have. But MobileNet is actively used in Google phones. A quick Google search can actually show you all these different networks and what the details of these networks are, and also. And here I'm showing a typical 2D object detection results, like it detects everything that are there. Now onto a 3D object detection, which is mostly a LiDAR based. So point cloud is what you call the output of a LiDAR. That's called a point cloud. It looks like a cloud, and these are all different detection points. The point cloud by itself doesn't have that much of a good information. So what you do is you combine it with camera, and that's what I'm showing here. So in the previous picture, if you see these 2D bounding boxes, but now you see these 3D boxes. These are the real boxes that you need, because now you have the depth information also, and you don't need let's say a stereo camera for this. You just have a single camera. Different networks again for doing this, and one problem that has been recently it's quite promising, and it's an open research area, is because LiDARs are pretty ugly to put on top. Then what people have done, or what some of the companies have done, and Waymo has a good paper on it, where they describe that they put LiDAR only for training and use LiDAR and camera for training the net. But once they deploy the model in the inference, they just use the camera. So that's one way. And one of the networks is the Avoid network, which I'm pointing it out here. Again, I would highly recommend this paper. The paper is pretty, it's a good survey. It's not very exhaustive. It's a little old, but it's a good survey, just to get an idea on what's going in the industry. And the third part is the semantic segmentation. This is another way of doing the scene understanding, apart from the 2D boxes and 3D boxes. And in a semantic segmentation, just to give a brief idea, and let me see if the video doesn't work. Okay, this was actually a video. But what it does is, like, it does pixel by pixel labeling. and it requires, think of it like an improved way of nearest neighbor clustering, if you want to see the original idea of semantic segmentation. A lot of different networks are there which are encoder decoder based. I'm not, this is just, encoder decoder is just one of the network architectures and the deep learning. A fan in, fan out is also, they call it. Segnet is a preferred choice of network that we usually use in production. And there's an architecture that is very highly successful, is the UNet architecture. I have not pointed it here, but UNet is a fairly good architecture. It was used to solve some problem in biology, and then they ported it into the autonomous driving. But if you do a quick Google search, you can find that UNet architecture. Again, to combine the semantic segmentation and the object detection in these two slides, there is a network that mask RCNN that combines these two ideas and then put it all together. Semantic segmentation, you can see it here. If you can actually see, this is coming from a paper, this video. But basically, what it is like you can see all pedestrians, and you can see the cars around. It's not a bounding box around the car. It's actually just somehow encapsulating just the car by itself. So it's very precise. It's very successful in the urban settings, like I said before. So now the last part of the talk, which is what are the challenges in autonomous driving. So first is the safety versus and the hazard that are there. Everybody knows, maybe majority of people might know the Uber case in Arizona that happened a couple of years back. The entire Uber autonomous driving has to be sold from Uber because the investors sort of pulled off all the money. So one accident is good enough to kill the entire program. So Uber is a good example of that. And they were using one of the safest cars in the industry, which is a Volvo. But somehow what they did is that they removed the Volvo's its internal safety unit that they had, and they replaced it with their own safety unit on top. So this was a case, in case people don't know, this was a case in Arizona where the car was not able to detect a walking a lady in her 50s and hit her and killed her. And in the reports later on showed that the car initially thought, when it was like around 150 meters or something, it thought of it like an unidentified object. And then later on thought of it as some other kind of an object. And then once it got more closer, it realized that the whatever the software stack that the Uber guys had, the network, the deep learning network that they installed, it decided to just neglect the object because they were not able to figure out what it is. And then in the last 1.3 seconds is when the Volvo's braking system came into picture, but that time it was too late. I'm talking like, and that was one sort of famous Uber case. You can read about this in online. There is an entire report on it from the national highways from the US authorities. And so right now we have this ISO 26262 standards that we have to comply. So that might answer that Raspberry Pi question. Raspberry Pi doesn't actually follow these standards, or any of these NVIDIA chips that are there, Jetsons and all these. They don't follow those standards, so we cannot use them. There are a couple of chips from other vendors that we use, and there are some chips that are internally produced. Those are the ones that comply. So we have to comply with these standards. But one interesting thing with this ISO is that because this whole machine learning in autonomous driving is such a new topic, ISO standard, this specific 26262 standard, does not have any machine learning guidelines by itself. So we have to, it's still a work in progress. Hopefully the new standards will be including it. Then the HARA method is another one, hazard analysis and risk assessment method, where they try to identify the system specific or the product specific problems that are there only at the software level. So the software goes through a multiple sort of checks, safety checks, before you actually put it into production. And then you have this ASIL, which is an automotive safety integrated level, which kind of sees the, pardon for my spelling here, it basically means risk classification scheme. it basically checks the number of false positives that are there. And that's very, very crucial, actually. If a neural network is able to detect an object, it should also be able to tell, you should also calculate the number of false positives that are associated with it. So that's important, especially while doing a classification. Because remember, this problem is not a balanced data problem. This is actually an imbalanced data problem. Now, the number of objects that you see are very less compared to the number of miles you've driven. So when you collect the data, there is a very small percentage where you actually see the object of interest that you want to train the network on. So here I talk about another famous Tesla accident that happened, where I think someone asked in the starting of this talk about one of those moon confusion that they had with the moon. In this accident, they call it a black swan issue. In the last point I'm saying that what the black swan issue is. What it basically is that somehow the accident happened, and this was one of the earliest accidents that happened. The autopilot just got collided with the vehicle that was stopped on the road. And if you actually see the feature map that the network is actually seeing, because you're able to visualize the feature map at least. What happens after the feature map is the part that's a research area. So when you see the feature map, somehow the height of the truck that was there, and it was a white colored truck, and it was a good amount of sunlight, all these things combined together kind of gave a very funny picture to the feature map that the network was not able to recognize, and then the car kind of got hit. And this network that they actually deployed later on, what Tesla claimed is that they have trained it on 130 million miles of data. So you can think of it like the key problem, that even though you have trained the network, there are still places where the deep learning or the machine learning has to actually fix things. Now, let's see. This is the last slide I have, where I just talk about what are the open problems so far that we have and things that we need to still work on in the industry on the autonomous driving. We still need to figure out the estimation and planning part of the AD, the autonomous driving. That's a part that still we haven't seen that much of success. The availability of the training data, any ML algorithm will need it. So simulation is okay for now, but there is a huge disconnect between the simulator and the real world data that we have. And the networks by itself, again, if anybody's interested, I can go into details of point 3, where I talk about improved generalization. It's basically based on the assumption, the basic assumption of a neural net is the data that you have is an IID, an independent and identically distributed data. That is a very dangerous assumption when it comes to putting things in real life. Because what you're assuming is that you have covered pretty much most of the scenarios, and the network should be able to now generalize. And when you generalize, the corner cases are the ones that are left out. So that's one problem. And the fourth point is the classic controllers that we have in the system in a car are very model based. For example, tracking an object is typically a Kalman filter is like the gold standard. So any new model that you bring in for tracking, you need to test it, or you need to compare it with a Kalman filter. If it doesn't work better than that, nobody's going to use it. So one way of sort of, again, an open research problem there is that if you can somehow, instead of having this a priori models with fixed parameters, sorry for my spelling there, it's fixed parameters. Instead of having fixed parameters, you can have actually adaptive parameters, and those adaptiveness can actually come from neural nets. So neural nets can actually, or deep learning can actually give those adaptive parameters a better approximation. And the classic controllers can work much better with those adaptive parameters compared to fixed one. That's one place. And the fifth point, like I previously said, ISO does not include the ML software standards. So that's something that needs to be sort of still done. We don't have standards yet for that. And then the last one is, which I feel personally, it's an upcoming research area, is the real-time computing, which is basically embedded machine learning. We need a very high-speed communication in the car, that's for sure, because of the data logging and in the data collection phase, and also when you are actually having the model in the inference stage, there are so many sensors into the car already that the amount of data that gets fed into the network onto the chip is too much already. So there is a lot of research that needs to be done on that part of how do you actually ingest that much of data. We need faster embedded chips for sure. And then 5G network, this is one point I wanted to add, just because in coming future, at least in maybe 2 years from now, there is a good amount of testing that's already happening where instead of actually putting things onto the car, you just connect it with a 5G network, and 5G is really fast. So there are ongoing tests going on right now in my company and in a couple of other companies, competitors. They're testing 5G networks to do the communication of the car, the sensors, and then the algorithm is on the cloud. And there is a good amount of communication between cloud and the car. So so yeah, that's all. I hope you liked it, and I'm open to take the questions.
Yes, sir, it is very nice session, very informative. I have also so many queries in my mind, but I would like to first of all, I might like to request my participants if they want to ask anything.
Mr. Tagi,
Yes.
you have described about 5G, and
Yes.
I'm thinking about the context in the context of India. There are some areas where there is no network, also mobile network, also in the forest, in the hill stations, also.
Yeah.
For that, what is the other solution we can use? Because I'm also developing something for this vehicle. So just I'm trying to find a solution for this. Can you suggest something?
It's definitely not going to be the 5G. I think for India specific, the way I've thought about it, and there are a couple of, so, I mean, just to give the problem a little bit of an outline, unfortunately, like the solving a problem from an Indian roads perspective is very tricky. So no player wants to get into it. But the good part is, because nobody wants to get into it, a minor improvement will make a bigger impact. So if it's not a 5G, what I would say is instead of doing it that way, probably you don't want to do a cloud and the car connectivity kind of thing. You don't want to do that for sure.
No, actually there is no network. So I'm thinking about multi-hop networking if we can do. So is it feasible? I think it is costly, expensive to set up a complete multi-hop network. So is it feasible?
I would say, yeah, I mean, it's costly. I mean, cost plays a bigger role in all these projects that we have. And so I would recommend, or probably what I would think on top of my head is doing everything onto the car by itself. Like the entire GPU and everything, all the computation is happening on the car and nowhere else. The car is an isolated system in the environment, and it's not connected to anything. That's what I would say.
Okay, and you are talking about the autonomous vehicle itself, but I'm developing a system which can be implemented on any regular vehicle, in low-cost vehicle also. So that device just I will fit in the vehicle, and it will work like autonomous. So I will use the CAN bus.
Or is it like the comma.ai kind of thing?
Yeah, something like that.
Something so comma.ai guys are doing that in San Diego.
Yes.
I know.
And the ISO standard for that, just I was asking about the Raspberry Pi. So ISO standard for that is not good, but the chips which are available, which are like army grade chips, that I am using for making my own PCB.
I see.
So what is your suggestion in that? Should I go for
what I would say is, like, one topic that I have not covered here intentionally is the one thing that we actually use while we deploy the models is the KPIs that we have, the key performance indexes. So one KPI is that's very commonly used by OEMs that they ask us to give them is the number of false positives versus the number of miles that you've driven the car. So you calculate that. So let's say you have it on Arduino or a Raspberry or some hardware that you have. You need to test it, and you need to test it. Let's take a number like 100,000 miles, or I don't know, like 1,000 kilometers. In 1,000 kilometers, how much is the misclassification happening? That needs to be calculated, And you really need, like, before you deploy it anywhere, that's the first thing that needs to be done, rather than actually doing it onto the car and then seeing the problem and then coming back and fixing, and then, you know, that loop is too long actually. So the best way of doing it is, once you have it onto your mainframe station, that whatever this workstation that you have, you would like to have some KPIs there. So I don't know exact details of your problem. Maybe I can, you know, if I have more details, I can probably get into it.
Sure. So for the testing, Miss, I'm using testing also, and for the lane detection, that system I found the perfect one. So
I see.
suggest some algorithm for the detection of human.
Oh, human. So, and we are talking only camera?
Yes.
Only camera.
Yes, only camera and human detection. I need software, so algorithm.
Oh, there are, like, I mean, use YOLO. I mean, that's like the easiest one. It's on Git. I mean, there should, and there is or use the MobileNet. MobileNet is, I mean, maybe I'm a little biased. My manager actually, me and him, we worked on it. So use MobileNet. MobileNet is a good one.
Okay, fine.
And MobileNet actually has, if you want to know, Andrew Howard is the guy. Andrew Howard had a paper recently where they're actually using it. If you go on TensorFlow and MobileNet is actually already pre-trained in TensorFlow right now. And so you all you have to do is just load the weights. So
okay, I was using TensorFlow actually.
Yeah, so the latest 2. I mean, I think after 2.0, any version after 2.0, they have the MobileNet now in the production in TensorFlow.
Okay.
So MobileNet, I would say, is a good option, because if you're using a Raspberry, you need to be very careful with the timings also, I'm sure.
Yeah.
Because that might be an issue for you. The biggest issue that even in my work right now, in fact, just before this actually presentation, I had a meeting. I was in a meeting. Real-time implementation is super hard. The timing is a big problem.
Yeah.
Like I mean, to tell you the truth, I mean, right now I'm fixing a FFT problem of how to speed up an FFT algorithm, and it's taking time.
Yeah, FFT is taking too much time actually.
Yeah. So yeah, I'm
and
fixing
the speed
that.
of vehicle, when it goes to up to more than 60 kilometers per hour, so it is difficult to manipulate everything.
Actually, that part. Now you're saying that. So if there is a company in London, forgot the name, but those guys are working with the F1 racing, and they want to do autonomous driving in F1 racing. Now, outside it looks very glamorous, but the inner part, the technical part, is very cool. What their hypothesis is that if you can actually run an algorithm on an F1 car, you can pretty much run it anywhere.
Yeah.
So yeah, that's I have the details of that actually. So if you are interested, I can probably get.
It was nice presentation. So I will get you in touch with you. I will take your contact detail from Dr. Richa. So
Sure.
I will be in touch.
Dr. Tyagi, this is Venkatesh. I'm from the industry, unrelated to any of this. But I have a question. How do you see, I mean, given the spends in this area around autonomous driving, and then there is also a parallel effort to launch flying cars, right? I mean, there are, I think, a handful of 10 or 12.
Sebastian Sun is doing that, yeah.
Exactly. So there are 10, 12 companies who are in various stages of prototypes and production equivalent. So, so what's the catch? I mean, which one will succeed first and faster? I guess is it more regulatory driven, or is it a technology thing?
Well, had I known this, I would have put my money on that. I would have clearly put my money on that stock.
Maybe I was trying to get some insight so I can put some money somewhere.
Let me know also, but yeah. No, but I mean, if I have to say it like what I see the trend going in the industry, what happened is that Tesla suddenly came in and made everybody to work on autonomous driving. So BMWs and Audis and I can only name the one that I closely work with, like all these German ones, and even Fiat and even the Chinese, some of the Chinese manufacturers, they just, because the customer is demanding, so they just want to put some sort of autonomy into the car for their next vehicle sales. So that's that. And then the research, and then the research part of that is flying cars can be one, but it's more of a hype, because investors' money is involved in it. I mean, I don't know if you're aware, but if you're aware of the typical Bay Area setup, one word is thrown around and every investor gets onto that.
Yeah.
So there is a reason why I intentionally don't work in the Bay Area. I mean, it's just too much. What I think is more promising, frankly, is the underground car. That's more promising, because think of it that way. Like, even if you have, let's say, a flying car, let's say, okay, you made it work and it's working. Who is going to leave his own car and then buy a new flying car? Why will you do that? So that's one problem. And then the other thing is, my view on all these things is like, I always give this example. When electricity actually came from Edison, there was a guy whose job was to light the candles on the street. That was an actual job. And then the electricity came in, and then everybody was like, well, the electricity is going to kill all the jobs and everything. And look at us now. Can we live? I mean, we can't even talk without electricity. So these things happen. So the transition happens. So when the horses were being replaced with actual cars by Ford, same thing happened. So I think these technologies not for us. I myself will never sit in a car like that, which has any code from me. So I don't think I'll sit in that, but it's mostly for the next generation. Like, I can see the next generation from after me, I can see those guys are very comfortable with taking an Uber and not owning a car. I still feel, I mean, ultimately we have to sell these things, right? Like that's why we're making a product. We got to sell. The customers, the old customers, or let's say my generation or even before me generation, they still have this feeling of owning a car. They just can't live with like, oh, can you live with a taxi for the rest of your life? The answer is no, most of the time. But the new generation people, they are okay with that. So I would say that's where the future trend is going, a subscription-based model.
Yeah.
But I think we'll be, I think we'll be very old by that time.
Sure, thanks. Thank you.
Yeah, no problem.
Dr. Tyagi, I am just thinking of just altogether different world when we have autonomous cars, some competition with the autonomous car.
Yes.
And I want to ask you some question about the customer feel. Okay, some people just love driving. It is for them, it is adventure for them. Okay, so what is your intake? What would, how will you target? How will the company is going to target or segment the? How will you target the customer? Whether they will buy this kind of product or they will like to drive by themselves only.
So this is the way company projects it, at least the way most of the OEMs, and again, OEMs are different from Tesla. Tesla's more, and I'm picking Tesla again and again because Tesla, like if people know it, it's quite common. And Tesla is not traditionally an auto manufacturing kind of a car. Tesla only has like what they have like 4 models now, but most of the Tesla has a different model. Tesla has its own car and own software. So they can do whatever they want to do with it. So most of the time, like what we face a problem is that we have the software, but the OEM is not ready to put it in their car because they don't want a bad name. So imagine you put a software, let's say on a Ford, and we had a collision. Somebody took a picture, put it on a newspaper. Everybody thinks Ford car is kind of bad. So we have to do a lot of things in there to sort of make sure that we are able to sort of they have company puts a big role on their reputation, too much, I think. But that's why Mercedes is a Mercedes sort of thing. But then I think people who loves driving and versus people who just want to, let's say, sleep while driving, it will be more of a feature. It's more that's how you actually pose it to the customer, right? That's how you pose it to the general public. That it's a feature. You want to use it, use it. If you don't want to use it, it's fine. It's like adaptive cruise control. It's a feature. But what intentionally or the hidden agenda sort of, I would say, is that people get used to it later on. People just get used to it. And then they get hooked onto it. And it's like you provide something for free in the starting, people get hooked, then you charge money. A classic business model.
So sir, this very interesting session that we have just, you have just presented the investigative framework for the autonomous driving, about the framework, about the determinants, about the barriers, about the challenges. And so it is nice to hear you, sir. And definitely I'm going to connect with you for the other sessions also. Okay.
Yeah.
Yeah. Answer one question is, one more question from my side, that although the company is thinking of all the dimensions, okay, because they need to launch this product. And also there is also the risk of human life also. So when the company is launching these kind of product, how much they are sure about that?
So let me take it to this part here. Yeah, that happens. So that comes under, have I included that? That comes under learning corner cases. And also there is something called ethical AI, which is, again, like there's a classic problem if you're driving a car and you see two people crossing a road, one is an old lady and one is a baby, and you cannot avoid the collision. Who are you going to pick to hit? I mean, so my vote goes with the old lady, but still, I mean, it's a little cruel. I understand, but it's like it's a little it comes in that last 1% thing. So most of the times the autonomous driving so far that has worked is like that 95% it works. But what about that 5%? So we call this ML for critical systems. So these are like critical systems. So most of the inspiration or most of the time a use case is the medical industry, where let's say you are detecting cancer. Even 1% misclassification can mean a lot. I mean, imagine you tell somebody you have a cancer and actually he was perfectly fit. It's kind of bad. So, you know.
So altogether, we need different infrastructure for adopting these kind of thing. Okay, because there is some anxiety among the people also. How they can.
That's always going to be there. I mean, that's just that's the role where the marketing guys are going to play. They have to polish it out nicely and all. I can only talk technical part, but actually, to just give you a brief answer to yours, the way it actually is the you're still on the. If I go to the first slide here or the first few slides, I would say till level 4. Yeah, there you go. Till level 4, it's okay. And right now we are on level 3, level 4-ish right now. So what can be done is like you have 95% success in your ML algorithm. The moment you see something is wrong or something is a little bit off, you just immediately give the entire control to the driver. That's all you have to do for now.
And sir, one last question from my side. What do you think, whether it would be more appropriate for the commercial use, or you will get the buyers for the personal use?
Oh, first it's going to be commercial.
Yeah.
Because again, it's the money involved there, and mostly the trucking industry is again maybe what I'm talking may not make sense that much from an India perspective. For example, hiring a driver for a truck is very expensive. The salary for a truck driver is almost the same as a master's graduate. It's like what, 80K or something, and that's expensive. So if you can replace, and driving a truck is a pretty straightforward operation as such. It's not an urban setting, it's almost a highway setting. And that's why I was giving that that example of that company. I really forgot the name of the company, but this is the one that drives a truck from Dallas to LA for United States Postal Service. And those guys are using it on trucks. So the truck is the first, and then it and then the luxury car segment, and then slowly it goes on like to the lower ones.
I think somebody has written the name AWS, no mobile.
No. It starts with NU, but
okay.
Yeah, it'll come to me.
Okay, so I think somebody has to make a Hollywood movie on how they are visualizing the scenario.
Yeah, cruel AI evil is coming and destroying everything.
Yeah. So thank you so much, sir. I think participants had really enjoyed your session, and we will definitely get back to you for different sessions also. And I also thank to Dr. Deepak, so because he connected me with you.
Okay. I want to thank Dr. Deepak also.
Yeah.
He's the one.
Thank you,
He's
sir.
the one everybody should catch in case there is a problem.
Yes.
Right. Okay. All right. So yeah, thanks everyone, and yeah.
Thank you.
Yeah. Bye-bye.
Okay, bye, sir. And participant, I will share the mail ID of Dr. Tyagi with you, sir, because people are asking about your email ID.
Sure, I'll give it.
Okay.
I'll give it. Yeah. I mean, I think you already have, so yeah, you can just pass it.
Yeah.
Thank you.
Okay. Thank you, sir.
Yeah, bye-bye.
Yeah, bye. And dear participant, I will share the information instruction regarding the quiz on your WhatsApp group as well as I mail you also. Okay. So most probably we'll start quiz by 1:30 p.m. tomorrow after the second session.
Thank you, ma'am.
So thanks to all of you, and you will get your feedback form on the ATAL portal only. So just be careful while filling the feedback also for this FDP.
It would be, ma'am, 100% positive.
Okay, thank you so much.
Yeah. Ma'am, when will be getting the materials of today?
Sir, I got the study material from Dr. Masood, the yesterday's session from about the cluster analysis. So I will share it in the WhatsApp group, and I will also ask Dr. Deepak, okay, and also Dr. Ganesh.
Okay. Yes.
Yeah, hi, ma'am.
YouTube recordings, ma'am.
Yes, sir. I will also share the links.
Okay, thank you.
Yeah, hi, ma'am. Tomorrow, when this evaluation link will get?
Ma'am, by 1:30 p.m. after the second session.
Okay, so and it will be, it will be how many minutes or an hour session?
Ma'am, we haven't decided it, but you will get at most 30 question MCQ type. Okay, and we are just in the process of deciding for the type of question or how many minutes we are going to provide. Okay.
Okay.
Yeah.
I will send all the instructions.